Welcome. Oh, it's loud. We sit. I'm Michael Altman. I'm the head of the Department of Physics at the HKUST. And as the head of the department, it is my honor to introduce today's speaker. Today's speaker is Professor Henry Tai. A little short bio about Professor Tai is that he was raised in Hong Kong, went to high school here, I believe LaSalle. From here, he moved to get his bachelor's degree at Caltech and then PhD at MIT. After that, he spent some time at the Stanford Linear Accelerator in California, as well as Stanford University and the Fermi National Accelerator Laboratory. From there, he moved to Cornell University, where he rose from assistant to associate to full professor and eventually to the Horace White Professorship of Physics. He joined HKUST in 2011 to become the director of this Institute of Advanced Study in this building, which is housed in this building. He's also concurrently a chair professor in the Department of Physics at HKUST. He asked me to keep this introduction short, so I'll just say that he's, with some other colleagues in the department, spearheading a new research group working in the area of particle theory and cosmology. And today he's going to talk about, the title of his talk is Our Whole Universe from Nothing, or in subtitle, How the Recent Breakthrough Observation of the Echo of the Big Bang Supports the Inflationary Universe Theory. Now you might remember from 2 or 3 years ago the great discovery of the Higgs boson, experimental discovery of the Higgs boson, and this was important because it verified a prediction that was made 50 years ago, which helps to understand the origin of our universe. Professor Tai is going to talk about yet another exciting experimental discovery, which supports predictions that were made 35 years ago. And the point is that we really live in exciting times where the experiment can now go hand in hand with the theory. And so that's all I'm going to say, and Professor Tai will tell you more. If you have questions, please, if you want to hold them till the end. Okay. We'll entertain questions at the end. Henry.
Okay. First thing I have to say is that this room is being used for a musical event called Intimacy of Creativity. That's why the piano's there, okay? I hope when we talk about, you'll find interesting also, and maybe not as nice sounding as the music you're going to hear, but at least hope to stimulate your mind, okay? So last month, actually March 17, a team of physicists, astronomers announced a new measurement, and that was splashed all across the news, every single newspaper you can find out. And I was told to explain why this is important. And the measurement was done in this so-called BICEP telescope. There's another one there called South Pole Telescope. And it's done by a team of 50 people, roughly. Now, what they're doing is they try to measure the microwave coming from outer space. We all know as you try to heat up a cup of water in a microwave oven, that water absorbs microwave very easily. But for this experiment, if they want to look for microwave from outer space, they don't want to have any water in the atmosphere. And the driest spot is send a satellite go to outer space. The second best part is go to South Pole. Is at the South Pole, where the air is very dry, and this is where the station is. And you can see that planes will land here during their summer, which is in a very nice warm weather of around 0 degrees Kelvin, 0 degrees centigrade. During the winter, it can get as cold as like minus 80 degrees. And furthermore, there's no sun. So the winter will last 6 months. And a few of them either intend to stay there for winter, or sometimes they miss the last flight. And then they have to work very hard for 6 months doing nothing else. It's very, very challenging experiments, obviously. And so the technology involved is very, very impressive. And I will come back to why this is so important. Okay? But the interesting thing is that in our International New York Times, which is Hong Kong version of New York Times, in the front page, when they report this news, they put somebody else, Alan Guth's picture in here, and in front of a telescope, which is for teaching purposes. And even though he's dressed with a thick coat, he's really never been to South Pole. Too cold for him. Actually, he said he'd never been to the southern hemisphere. But in any case, but the reason they have put this in front page is a story that I have to explain to you as well. So, the universe. First, the title I have to explain step by step. Okay? The first, of course, the universe. Well, there's many definitions of universe over time. As we go along, our definition gets more and more precise. But a very nice definition is what the Chinese people have, Zhangzi, 2,000 years ago, which is called 宇宙, which means really space and time. And I think that's actually a very, very philosophical and appropriate definition, that the universe, it means all of space-time, and of course, everything in it. But in particular, origin and structure of universe for a long time, ever since the human civilization. In the early days, this topic was dominated by religion, astrology, philosophy, which in turn was heavily influenced by culture and politics. So, for example, 3000 BC, the Hindu, the universe is oscillating. Babylonians believe heaven and earth form a single unit, which is, you want to ask the question, what's heaven? But by then, at that time, they mean whatever they can see up there. Of course, the biblical religion believes in the Genesis creation, and also Muslim philosophers believe that universe was created as a beginning. Okay? And of course, one can also think about universe to be infinite, timeless. And there's all these different ways of thinking about the universe, and mostly from the point of view of philosophy. Later on, a group of people, Aristotle and others, come back with a more sort of precise definition. Okay? This definition is quite natural. In fact, considering a baby surrounded by parents, grandparents, in China, uncles, aunts, and Hong Kong nannies, the baby would think he or she is the center of the universe, which in some sense is not incorrect, right? And so, in early days, China is called Middle Kingdom, and the emperor is called the Son of Heaven. Again, you like to put yourself in the center. And here, they put the Earth to be the center, with the sun and other planets moving around the Earth. And that's one picture that have been adopted by the West. However, around the 15th century, Copernicus and others beginning to think that maybe the sun is the center. Okay? So in this case, the sun is the center, and the Earth is moving around the sun, everything else moving around the sun. And Galileo, we all know, invented a telescope and used it to show that that's really true. That means Earth is not the center, but it's orbiting around the sun. But he got into serious trouble with the Roman Catholic Church, which prevent him to talking about this point of view for many years. However, this is essentially what we believe today, and Newton is the one who put this in a solid ground. So we all know that the story about a tree in Cambridge. Still, this tree is there, probably descendants of Newton's tree, with an apple falling down. And Newton tried to understand why everything will fall down to the surface of the Earth. And from this, he came up with the gravitational force theory, which is very well studied in high school and maybe in mechanics. This actually works very well to explain how the planets orbit around the Earth, the Sun. Okay, and it has been very, very well established within the realm of our solar system. Now, over time, we're beginning to see that the Sun is really not the center, but rather it's somewhere around its arm. This is not our galaxy, but a galaxy similar to ours, because we can't take a picture of our own galaxy. Somewhere around the arm, and there's many, many stars in our galaxy, our own galaxy. So if you look out the sky when you see the Milky Way, that's where you look at the center of the galaxy. When sometimes you look at the sky, hardly anything, you're looking at a direction away from the center. So our galaxy is very similar to this type of galaxies, and our Sun is one of the billions of stars. Okay. We're also now beginning to know that there are many billions of galaxies in our universe. Okay. Our significance is decreasing over time. Okay. As from my talk, you will notice that step by step, our place in our universe is become less and less impressive. But to worry about these big numbers, so there's a very convenient way to write numbers which are very big or very small. So I just want to introduce to you some of them you know very well. For example, if I take the speed of light, which is 300 million meters per second, very, very fast. And I should say that nothing moves faster than the speed of light. It's usually we write as 3 times 10 to the 8th meters per second. So you can count, there's 8 zeros there. Okay? And that's a simple way to write a lot of time, because when we deal with very big numbers, it's easier to write this way. And 10 to the minus 3 is 0.001. 10 to the minus 35 second is this. And obviously, this is much better, because this you count. You're not careful, you can miss or miscount. Okay? So that's why we all like to write this way, easier, more to read, and less likely to make mistakes. So we're going to use very big and very small numbers. And 10 to the minus 35 seconds is going to appear again and again. Okay. So I have a number of lessons I have to at least tell you. And the first lesson is that following Einstein's theory of special relativity, you must have seen the formula E equals mc squared. Okay. Even if you don't know where it comes from, that's okay. All you have to do is that what this formula means that energy and mass are more or less equivalent. So for example, in fusion, hydrogen bomb, atomic bomb, or nuclear power plant, you convert a little mass to energy, and that's how we can get many sources of energy from nuclear power plant, mostly because C is very big. Okay? So a little mass can be generate a lot of energy. A bottle of water, if I can convert it all to energy, that would be enough energy to supply China for half a year, maybe a year. Okay. Okay, so I'm not going to introduce any more formulas. I know this is not meant to be a technical talk. Okay. Now, here comes Einstein. Newton tells us that planets will move around the sun in his gravitational force law. So Einstein was trying to combine special relativity, which he discovered, together with gravity, which Newton discovered. And he asked the following question, very simple. He said, since there's nothing in between the Earth and the sun except empty space, how does the Earth know about the gravitational pull of the sun? Right? I mean, you may have asked that question, only that you are 100 years too late. But Einstein thought about this, and he realized that, yes, there is space. So space can be used to explain this. And from that came the theory of general relativity. Okay? And the lesson 2 is that to explain in the full glory of the theory, but we can think a little bit about, say, on a mattress. You put a bowling ball on a mattress, then the surface of the mattress will sort of be a little bit depressed, as shown here. And if you introduce a marble, will follow the curved surface of the mattress and move towards the bowling ball. Now, if you can't see the mattress, you would think that there's a force pulling the marble to the bowling ball, interpreted as gravitational force. But Einstein say really is that it's due to the curved space in this picture. And of course, to imagine what happened in 3 space plus time is very difficult, and I have never been able to do that. But fortunately, Einstein tells us that once you get the picture in this simple case, then in more complicated cases, he will provide the mathematics to lead us to make very precise predictions and calculations. So this is the way how the planets move around the sun, okay? Because of the curved space-time. And from Einstein's point of view, space-time is very active. They can warp, curve, expand, shrink, do all sorts of things. In fact, can behave in a way such that a black hole, space sort of disappears in some ways. So this is a way to imagine in a very simplistic lower dimension case how general relativity tells us. And of course, you may know that GPS require Einstein theory. Newton's theory is not good enough for GPS. If you use Newton's theory to put it operating on the GPS, the measurement would be totally wrong. So already we know we need curved space-time in order to really do precise measurements. So Hubble, in 1929, discovered a very simple fact again. That means that the universe is expanding. That what he saw is that for galaxy further away from us, then you will move faster away from us. Okay? So this is, again, instead of 3-dimensional picture, I draw a surface of a balloon, and that's expanding. You can see them expanding. And here we put coins on the top. So you can see here, this is, say we live here, and this is 2 galaxies. And as the balloon expands, the one that's closest to us move away. The one that's further away move away from us faster. Okay? That's essentially what Hubble saw. And the only interpretation sensible, besides the one that we are the center of the universe, is that the universe is expanding. Relatively quickly, that our universe is expanding. So now we have to come back to our universe today. Before I have to go back to the data, to explain a little bit today what our universe look like. Okay? Everything we see outside, atoms, molecules, photons, electrons, we call matter. Okay? The Earth is made of matter, the sun is made of matter, the galaxy is made of matter. These are all matters. And question is, what else is in our universe besides the matter that we can see, or the matter that we know is made of atoms, molecules, electrons, photons, neutrinos. And turn out, surprisingly, there's something called dark matter, and there's something called dark energy. Here I have 73%, actually more accurate measurements like 68%, but essentially only 4% of the energy content in our universe, what we know, atoms, molecules, photons, neutrinos, things like that. Dark matter is mysterious, and dark energy even more mysterious. This is obviously an area that requires a lot more work to understand what's the 96% content of the universe made of, because we more or less understand the 4%. Okay? So everything we have been doing is essentially focused on the 4%. So now we have to understand the rest. Now, if dark matter is dark, we can see it. Dark energy is dark, we can see. I mean, how do we distinguish the two? Okay? And I'm explaining this partly to give you an idea of what our universe today is, but also we will lay the foundation for what we need later. So think about the following. Okay? I have 3 atoms or 3 galaxies. Either way is fine. Okay? And as the universe expands, this volume expands, then they will be further separated. And what it means is that the matter density is decreasing as the universe is expanding. I think that should be clear to everybody, right? The amount of matter is conserved, so you have a larger volume to accommodate them, then the density will go down. Now, this is matter. Doesn't matter ordinary matter that we know or dark matter that we don't know exactly what they are. The blueness I would describe as dark energy. Okay? The more blue means more dark energy density. Okay? So as the universe expands, the dark energy density does not change. Okay? That's the difference between dark energy and dark matter, and that's why we can tell them apart. Okay? So what does that mean? Well, this is dark energy times this volume, and this is dark energy times this volume, but the density is the same. So in some sense, the dark energy has been increasing. Okay? How is it possible that some energy density will stay constant while the volume is increasing? Okay? And this is another lesson of general relativity, which is very mysterious even to me today, but Einstein theory just gives you that answer. So what can we do, right? And Einstein general relativity gives us 2 points. The dark energy density will have negative pressure. Okay, that's why what I described can happen. You know, radiation usually have positive pressure. Almost everything you see, touch, have positive pressure. You never worry about the sign of pressure because anything you encounter is positive pressure. But dark energy have negative pressure. And also, because of that, the expansion will become exponential. Okay? Now, I will explain the word exponential later. At this moment, all you need to say is that expansion in the universe will become very rapid. Okay? So, as the universe expands, we start out early in the past. Yellow is ordinary matter, red is dark matter, and the blue is dark energy. Now, the density of matter will be decreasing as the universe expands. And so, but dark energy density don't decrease. So over time, the universe will be dominated by dark energy. Okay? This is probably the future of our universe, as far as we can tell at this moment. Okay? Most conservative belief. Okay, so 2 things, and the universe expansion will become exponential, will be much more rapid than it's expanding today. Okay, so that's another message. So that means that as the dark energy becomes more and more important, the expanded universe will be accelerating. Okay? And this is exactly what 3 groups of astronomers observed in 1998. Okay. Very, very surprising in some sense, but by now it's very well established. They were also given the short prize, of course, before the Nobel Prize. The dark energy is most likely the vacuum energy. That means that the vacuum we have, we think it's vacuum, but actually there's some energy density there. And this is what Einstein introduced a long time ago, about 100 years ago, and then he abandoned it as well. One property that will come back. Okay? So, if the universe is expanding and cooling today, then that means if we go back in time, it will be smaller and hotter. Okay? And it had to be hot enough such that you can produce the nucleus, helium, lithium, beryllium that we know, so that you can calculate when they produce, how hot it gets, and what the temperature today should be. And the prediction is that the universe should have a temperature which we call 3 degrees Kelvin, or in centigrade is 270 degrees negative. Okay? This is the temperature of our universe today. Now, of course, this is very, very cold. But Kelvin means that the absolute temperature is, you cannot be lower than that. So 0 degrees Kelvin is minus 273 degrees centigrade. So that means that there's still a temperature, a very, very minute temperature, but we're still living in a thermal bath of that temperature, okay, 3 degrees. So now I'm going to give you a little lesson on quantum mechanics. If you don't know quantum mechanics, I just take what I said on face value, okay? You just have to know at least a very basic point. That means, say, an electron is a particle, but it behaves like wave. Light are waves, but it is collection of photons, particles. We cannot have half a photon. We cannot have half electron. So they're particles. They come in integer numbers of photons or electrons. So that means everything behaves like particles. But single particles also behave like wave. Okay? And wave takes some size, and they fluctuate. And for that reason, a hydrogen atom or any atoms, you would say the electron would be attracted to the nucleus and fall in, and then we have no atoms. But because the electron behaves like wave, it will be moving around, fluctuate, so it can never go all the way down, and as a result, we have atoms. Essentially, that's why we're around. Okay? And that's because of quantum physics. So this is a very, very simple picture of looking at physics correctly. Okay? I simplify it, but I did not cheat on you. Now, because of quantum mechanics, no matter what you look at, if at temperature, then there will be a spectrum. So if you look at the sun, the core of the sun is roughly 5,000, not the core, the surface of the sun is roughly 5,000 degrees Kelvin. Well, you know, Kelvin and centigrade are more or less comparable when the temperature is very high. And the spectrum is given by this curve. And Planck is the most famous German scientist, or most of you know the Max Planck Institutes. And you ask, what have Max Planck done? And Max Planck have given us the formula for this. Okay? That's essentially what he's done in his whole career. Most important. He gave us this formula. And so that's why for the sun, this is where the light are, and this is longer wavelength, and all the way down that way would be microwave. Okay? And this infrared here, and then this X-ray. And for the sun, the peak intensity of brightness is at around the wavelength where our light are. And that's no surprise that we adapt to that. We are most sensitive to visible light. Okay? But as the temperature goes down, the curve goes down, they never cross, and then this is still very high. But imagine 3 degrees. 3 degrees would be really, really just lie on top of this bottom line. Okay? But still, you can calculate. you can precisely find out what it is. And that's exactly what people try to measure. The 3 degrees Kelvin, there's a Planck's blackbody spectrum. It will peak around microwave, and 2 physicists, Penzias and Wilson, measured a microwave length of 7.35 centimeter. And this is wavelength more or less comparable to what you use for cell phone. And they work in Bell Lab, ATT Bell Lab. And people want to use microwave for communications. Instead, they discover that if you look outer space, there's always this microwave that you cannot get rid of. Okay? It's always there. And so now people have done a much better measurement. Okay? And for the blackbody spectrum is given by the green curve. This is done by Kobe in 1992. And what Penzias and Wilson measure is this wavelength, and they see this height. It's all exaggerated. And all the crosses are essentially the measurements done by satellite Kobe. Okay? There's about 1,500 scientists, engineers involved in that experiment. And they got a temperature. By now, the temperature is very well measured. This is the temperature, the bath is very, very precise. And this is the data fitting the curve, very, very precise. One cannot but be impressed by how good it is. But in fact, I've cheated you. The reason is because these error bars are not real. Okay? The actual error bars, if you put it, they would be so small that they will just sit inside the curve. You can't see the data points. So instead for you to see the data points, they blow up the error bars by a factor of 400. Okay? So this is really, really amazingly accurate measurements that can be done. So this, plus a few other experiments, observations, surely proved that Big Bang is correct. Okay? There's no doubt in anybody's mind who's working in this field that in our universe. And we can also tell the age of universe now is pretty well measured. There's some error bars, but it's roughly 13.8 billion years old. Okay? So we're no longer, but rather getting rather precise measurement of the age of universe, what's the temperature outside, and a number of other things. So this is the picture of the Big Bang. Essentially, this is time, somewhere origin, and then around 1 second on, we know pretty well that the Big Bang cosmology explains everything very well, fits very well. Okay. So now we want to know, go back, okay? Go earlier time. One way to go earlier time is to recreate the early moments of the universe, and this is done by the CERN experiment to collide proton-proton, and they can roughly sort of reach 10 to the minus 15 seconds of the universe, okay? And that tells us some properties, of some hint of what happened there. But still, we want to ask the question, how did the hot Big Bang start, right? Big Bang is the biggest explosion ever. It created our whole universe. So if you have explosion, you must really convince yourself or curiously ask why it happened, what caused it, right? And today, the belief is that it started with the so-called the inflationary universe. The universe inflate, and that's what I'm going to explain, okay? So roughly speaking, it's the following. Universe starts from a single point. I mean, people like to use bubble, but it's so small, I would just call it a point. Very, very small, okay? And the total energy of that is much, much less than a single electron. And that point is filled with the much higher dark energy than today's dark energy, but still not infinite. It's big, but not infinite. And then that point will grow exponentially. Again, I will come explain exponentially in a moment. During the inflationary phase, with the dark energy density staying more or less constant. So the dark energy is very big but constant, and the universe just expands by many, many orders of magnitude. Okay? And then, at about 10 to the minus 35 seconds, inflation ends, and all those energy now can convert to radiation matter that began our hot Big Bang universe. And those will be the particles that we see today, plus dark matter. Okay, so this is the inflationary universe picture. Okay. Now, what's exponential growth? Okay, so let me explain what exponential growth is. So this is a famous story either in the Western culture, Chinese culture, is that if you want to, I don't know which version you heard of, but roughly speaking is that if you put 1 grain of rice here and 2 grain here or 3 grain there, and then of course 64 squared, by this time you were 64 grains, and the total number of grains of rice you can put in a hand, okay? A handful. This is just what normally how you grow. Exponential we call doubling, okay? That means that you put 1 grain here, 2, 4, 8, double, okay? And that's called exponential, or doubling, okay? That means it's much faster. So the first few is comparable, but it grows much faster. Okay? How fast? Well, if you do, here is 1 square is 1, 10 square, you're already 2 to the 9, and then you start 19 square, 28 square, and then when you reach the last square, the number of grains is essentially more than this is size of the Earth, okay? So that's how many grains you need, okay? So that means that if you do exponential growth, it will really grow rapidly, very, very fast, okay? And 64 is roughly the number of doublings that our universe encountered during the inflationary phase, okay? Order of magnitude. Now, as we say, as the universe expands by that much, the energy density stay the same, dark energy, then all of a sudden we have a lot of energy we convert to matter. That's why we have all the stuff, stars and galaxies in this universe, right? And the big question is, that means everything, including space, comes from nothing. So my definition of nothing here is that not only there's nothing, but it's not vacuum. Vacuum still have space. Here is not even space, okay? So that's truly, absolutely, there's nothing. One can even ask, if there's no space, is there time? I don't know the answer to that, but I'm not sure. If you can't measure, it doesn't really have meaning. So now, the question that many people ask is, what about energy conservation? Right? I mean, obviously, this is so important nowadays that we need energy. We have to generate energy from some source to some other source. And this way, it seems that we get something from nothing, which is true. But question, what about energy conservation? And the answer is, energy can be conserved if and only if the total energy of our whole universe today is exactly 0. Right? So we start with 0, and today is 0, and 10 billion years ago is 0, and 10 billion years from now is 0, then that's okay. Right? Energy is conserved. I think high school you learned that too. And the answer is, that's exactly what we expect. That's exactly what's predicted by this theory. The total energy of our whole universe at any time is exactly 0. How is that possible? So this is lesson 9. But I point out, lesson 9 is a lesson that you sit down, you can figure out yourself. Okay? I just outlined to you how to figure it out. And a high school who knows something about capacitor will be able to answer that himself. So roughly what happens is the following. We know the capacitor, right? You have a capacitor in the electric circuit. You have positive charge on one side, negative charge, and there's electric field between. plate is big enough, no electric field outside. And then the two plates, opposite charge, will attract, right? Electric force, opposite charge will attract. Now, if you have two plates made of mass, the gravitational force will attract them. But mass and mass is the same. So it's the same sign attract. Okay? So you won't be surprised that you store energy in electric field. It's positive energy in electric field. That's how you can store energy in capacitors. But the energy in gravitational field is negative. So whenever you have a mass, you have gravitational field around it, and the gravitational field energy is negative. Okay? And for that reason, everything in our universe is matter plus gravitational field energy, so it's positive and negative, they can add up to zero. Okay? And the difference between gravitational field and electric field is that electric field is opposite charge attract, gravitational field is same mass attract. Okay? And that tells you why the energy in gravitational field is negative. You can think about this picture and you can convince yourself that's what happened because the plate move towards each other. Some plates with electric field become none, but the energy converted kinetic energy of the plates, and the opposite. So you can go home and work it out, okay? So because of the negative gravitational field energy, you can convince yourself that it's possible that the total energy of a universe at any time is exactly zero. In fact, when we start the calculation follow general relativity, that's essentially is built into the calculation. Now, once we have that, still we have to ask why inflation? Okay? And the reason we need inflation is to solve some problems. For example, one of the problems is that in late 70s, we realized that a very beautiful popular theory called grain unified theory, still unproven today, that predicts the existence of monopole, magnetic monopole. So we all know magnets have north and south pole. You break it up, still north and south pole. That means that it's made of dipoles. There's no only north or only south. But in the 70s, we have theories which can produce monopoles. And then you look at hot Big Bang, you think you will produce a lot of monopoles, and then we haven't seen any. So that's a problem. And inflation will be able to solve that problem. Okay. But of course, not everybody will be convinced. One of the many criticisms, because to do inflation, we have to go to 10 to the minus 35 seconds. We do all sorts of things. It's a wild speculation, crazy, all question. And one of the famous astronomers, Martin Rees, put it very nicely, okay, as a criticism. And he essentially said that he's a skeptic, of course. He says skeptics about exotic physics might not be hugely impressed by a theoretical argument to explain the absence of particles that are themselves only hypothetical. Preventive medicine can readily seem 100% effective against a disease that doesn't exist. Okay? So clearly, inflation will try to explain things, but people will also have a lot of questions about it. The inflationary universe also solves two other problems besides the magnetic monopole problem, as pointed by Guth. The picture I show you in the International New York Times last month, front page. He also solved the flatness problem, explain why the universe is so flat, and the horizon problem, why the universe look very similar in all possible directions. Okay? And that's beginning to convince people that the whole picture I described is really quite meaningful. That is, all matter comes from inflation, and space created by inflation, everything coming from inflation. The original theory has some little glitch to it, and Andre Linde sort of solved that technical problem. Yesterday I was preparing this talk, but I was distracted by Andre because he's criticizing some point that my student and I made, and then we have to respond to him right away. So we start this argument over time, and will take a while. And this is typically how theoretical physicists interact with each other. You do something, somebody challenge you, you try to defend yourself. And if you can't defend yourself, you change your position. If you defend yourself, then you can move on. Okay? And that happens on a very regular basis in our field. And this is what's called the ultimate free lunch. Okay? Everything from nothing. Now, of course, there is something I should point out. Okay? The something is the laws of nature. We have the laws of nature, of physics, of quantum physics, of general relativity, of particle physics. And it's from those laws that we can deduce what happened. Okay, so when I say nothing, in terms of physical nothing, but conceptually and in terms of logic, there's laws of nature which guide us what happened. So now let me repeat about the inflationary universe to tell you the picture now. So we start from a single point of very, very tiny size with total energy tiny, okay? And this point could have coming from a quantum fluctuation. Quantum physics perfectly allow a quantum fluctuation from absolutely nothing, okay? And that point will grow exponentially, doubling many times. And at a certain point, 10 to minus 35 seconds, it stopped. And then, because you have a large energy density, now multiplied by this tremendous light volume, then you have a lot of energy. And then you can convert that energy to radiation, matter, start the hot Big Bang. Inflation ended when our observable universe is of the size of an apple. Remember I say the universe age is like 13.8 billion years ago. That means that light from the beginning travel to us take 13.8 billion years, light years. Okay, so those light or microwave reach us are coming from the beginning of the universe. The actual universe today is bigger because while the light is reaching us, the universe is expanding. So the size actually of our observable universe is roughly 42 billion light years. Okay, very huge. At the end of inflation, what we observe is the size of roughly an apple. Choose another favorite fruit you want. Orange is okay, grapefruit is okay. Okay, choose your favorite fruit. However, in order to start from this droplet, okay, our observable universe is a tiny fraction of actually the whole droplet that start fluctuate from nothing. Okay. So this tells us how small, how peripheral we are. Okay. Now, the whole general theoretical picture was essentially completed in 1983. Okay. At that time, we have a theory, we can do calculations, we can play around with it. It's a philosophical. Some people really like it, embrace it right away. Some people think it's crazy, stupid, cannot be right. And the schools arguing. You can go to a conference and there will be hot debate arguing. Okay, a lot of time more reflection of personality than the physics behind. But you can argue and argue. The important thing now is that we are doing science. We can make predictions, and then we can check if the predictions are correct or not. So the whole thing is that during inflation, there's fluctuations. And fluctuation can introduce fluctuation in the density, in the temperature, and some of the fluctuation will eventually lead to star and galaxy formations. And sure enough, the temperature fluctuation is what's been detected. Okay? It's very small. It's roughly the range. It's tiny little range of fluctuation. Okay? And on average, it's really 1 part in 100,000. So very, very small. So really impressed that people can measure that. So this is what happens. If there's some density fluctuation, and then universe will grow and then cool off, the fluctuation, the high density will become higher because other things will pull by gravity towards them. And so eventually, they aggregate, cluster to form galaxy and star. And that's essentially the universe we have today. And you can do numerical simulations to check how correct this is. How does that agree with our universe today? And it's very, very impressive that this picture agrees, okay, with what inflation predicts. But we can do more. So as I say, COBE measured the temperature difference. So the different color indicate the temperature difference. And then later on, a WMAP, another satellite, measured better. And then the Planck, which do even better job, okay? So roughly a span of 20 years, this is what's first measured, and then this is what measured last year. Okay? So this is the temperature difference. So this difference is measured by COBE, and very impressive. And this is what's measured last year. And you can see this is much, much better than this. In fact, look at this map. You look at the resolution is such that if this is the surface of the Earth, you can identify Clearwater Bay. Okay? That's how good it is. Okay? Of course, that is difficult to compare between predictions, theory, and experiments. So we generate a curve. Theory calculate a curve of analyze the data to show in a way so that you can compare theory experiment. And this fluctuation is, these are data points. The green is the theory, okay? And the only thing I can say is that this is spectacular. Spectacular in the experimental measurement compared with theory, and spectacular in the sense that the people can actually do measurements that accurate, okay? Remember, this is 1 part in 100,000 in terms of temperature, okay? So very, very tiny changes that it can do such good measurements. Very impressive. And I should say that a lot of people is convinced that inflation must be correct, okay? So the number of people who believe inflationary universe have been growing, but still there's a few holdouts, very much like global warming. You know, there's always somebody who's don't believe it. Okay? I should point out that besides that curve, there's other curves which I didn't have time to show, which also agree very well. So now I come to BICEP, what they announced last month. What they measure is the polarization of the light microwave arriving. So you know that light or microwave have polarization, and that's linearly polarized. And what they measure is the polarization. And polarization actually can be decomposed into two types. Both are linearly polarized. One is this type, the other is this type. And the difference is that if you look at a mirror, anti-clockwise would be burned clockwise, while this one, you can't tell the difference. Okay, so this is how it's decomposed. And of course, polarization of light is very well known to you. If you have sunglasses, you know, all the light coming, reflected light will have polarized this way, and then your sunglasses try to block it because they're not good for your eyes. And so it's something that is quite easy to do, but to separate these two is where things are difficult. So the BICEP people measure this. This is a polarization map. The color is that the red ones are, one is clockwise, one is anti-clockwise, okay, roughly, okay? And they are looking for this B-mode polarization, okay? E-mode have been observed already. And that's what they see. So they announce it of the observation. Why is it important now, okay? The importance of this polarization is that inflation predicts the existence of these polarization and have a very well-determined spectrum, what it looks like. Okay? And what they measure is agree with inflation. But what's more important is there are people who try to find alternative to inflation. There are people who don't believe inflation, and they want to find alternatives. And some of the most prominent alternatives predicts there's no B mode. Okay? So this is actually rule out these alternatives. Even the alternatives look very ugly, but still, you don't know. Okay? So it's very important to show that these alternatives are probably wrong. And the third thing is very interesting is that these fluctuations coming from a quantization of space-time. So a lot of people think space-time is a curve, their background, they should not have to be quantized. We can treat them as classical. We only quantize what we see, particles. Okay? And this actually shows that space-time is also quantized, also obey quantum mechanics. Okay? Now, I should put a word of warning, which are also trying to compete. They are fierce competition. Who get this out first? So I list Planck, which have a lot of data, which I don't know why they haven't announced it. You know, that's a few hundred people's collaboration. That's a satellite. And then there's ACT in Chile. And then there's this, for example, is a balloon. There's many other experiments also try to do this. And they will have a lot of data coming out. And they will either confirm BICEP. I think there's a good chance they will confirm it. Or they will confirm and show more detail. Or maybe they find BICEP have little problem. So we don't know. Okay? So we should wait. Okay? But these data should come out very soon. In fact, Planck said they will announce their result in October 17th. So I think the other group will tell you when they're going to announce the result. So we just mark the calendar, and then at the time, we're just going to go online and look at the press conference. So the BICEP was originally started by Andrew Lange, but unfortunately passed away. So the collaboration was led by 4 young people. Young, they look relatively young compared with usually a senior person leading. And from Harvard, Stanford, Caltech, Minnesota. And one of them, Shaolin Ku from Taiwan and Stanford, is coming next month to attend our cosmology workshop. So I think it has been very exciting in cosmology in the past century, from totally speculation, wild guesses, to become precision science. And I expect more exciting discovery coming in the coming decades. And we are lucky to be living in a time with human civilization of thousands of years, that we are living in a time that we know how our universe started. So, thank you.
Thank you very much, Henry. I think if you have any questions, we'll be willing to answer them or try to answer them. Anybody? Questions? Oh, here you go.
Very, very nice. But knowing how modest you are, you didn't say much about your role in any of this at all. You quoted Alan Guth a couple of times. I think it is only fair for you to say a little bit about what you have done. Okay. That's a serious one. I think you should.
Well, I think many people have contributed to the field.
That's not my question. Say a few words, please.
I was working with him on a monopole problem, so we used that to solve the monopole problem. So I would say that monopole problem is a problem that you cannot get rid of because you can show it's produced a lot. But the other two problems, actually, some people don't believe it, like Penrose don't believe it, because you can always choose the universe to start with very flat, very homogeneous. So, but it's all a matter of taste. Even today, there's still people who believe inflation cannot be correct. But we have to wait. Yes?
So if the whole universe from very tiny point, and now the whole universe, you have so many unpredictable randomness. So my question, because 10 years ago, you talked about string theory, and you said you believe string theory was correct. My question is, could there be more theories, maybe infinite number of theories, all correct? Because see, this Big Bang, the randomness is enormous. So how do we know there is only one theory could be right, or there should be infinite number of theories could be equally right?
I should say, when I say inflationary universe, I don't mean that that's a very precise model. Okay, it's really like a paradigm. So there's many, many models. And I'm sure that this room, probably at least 5 or 6 people have their own models for inflationary universe, okay? And the predictions are essentially more or less universal among all those models. That's why we present those predictions. Very specific models may have specific extra predictions in more details. So that's what we are very challenging, people working on. So I would say inflationary universe is like a paradigm, very much wave-particle duality in quantum mechanics. When de Broglie proposed wave-particle duality, he doesn't have equations. But there's many experiments you can do to see if that's correct or not. That's more or less inflationary universe status now. So I think there's a lot of work to be done, more discovery to be made, more measurement will be made. I think the next satellite is under planning already. And many experiments continue being upgraded. So we will know a lot more. And hope that in another couple decades, we can really pin down which inflationary model is correct. And that's the work that we are working on now.
Donald, please.
I have a question on a philosophical paradox here. Because on the one hand, we really know nothing about the dark energy and the dark matter. And of course, we know nothing about what happened in the first 10 to minus 43 seconds, how the inflation started, what's the driving force, and why they're doubling so rapidly. But yet, on the other hand, we find from this experimental and theoretical calculation, based on the satellite measurement, and look at the fluctuation of the microwave, constant microwave background, it fits so well. So it's really a dilemma to me. When I had a theoretical basics so rough, so undetermined, and yet you can produce such good feeling. So there must be something wrong there.
Well, it probably just means that the data are not precise enough, okay? And as we get better and better data, of course, we will blow up this region to much finer, and we can see more features. And this is only one curve I showed, which is temperature. And then there's E-mode polarization, EE, ET, BB. So there will be more data coming from different angles, and then one can pin down more precisely what's going on. But those are details. The overall picture, I think, is becoming very robust now.
Okay, the question goes with the microphone.
Thanks for your talk. It was really interesting. It's not my expertise, but I'm wondering how we can get close to an experimental validation for nothing. What does exactly nothing mean? Or is it possible to experimentally prove the theory of quantum physics that we can get matter from nothing?
Well, in a sense, what I'm showing the data is, I won't use the word proof, but I will use the very strongly supporting, okay? Steve Hawking would say that data, even before this, that's data not as good. And Hawking, who embraces inflation, would say that the data overwhelmingly support inflationary scenario. So, and then that was even like 10 years ago. So the data get better, the precision measurements get better, and then agreement gets better. So the way we have is the same with general relativity. You have a theory, then you write down the predictions. And the predictions more or less written down 20 years ago. So it's not like you see the data and you try to fit it. So you make a very precise prediction, and then you wait people to go and measure it. And if the agreement is very, very good, like here, then you tend to believe what you are working on. And then after repeated comparison between experiment and theory, at a certain point, you will accept it. At the same time, you try to find alternatives to fit the data. And that's what people are trying to do also. And then the alternatives typically very ugly, and then ugly and wrong. So that's what's happening.
Ian's next. Okay. Wait for the microphone. Yeah.
Yeah, very beautiful work. And of course, all these concepts are very difficult for even other scientists. We would still regard ourselves as lay people. But maybe a couple of very quick points I want to probe you on. When you're saying about nothing, And then you talk about matter and energy. Now, the Einstein equation relates the two. But the thing is, the things that are massive, the things that we think are real, they are negative energy, right? Because that's potential energy that could be converted. So when we have a nuclear reaction, we take mass and convert it to energy. So is that how you end up with nothing?
Yeah.
Like a plus and a minus, that the mass or the matter is actually negative versus what you would call energy.
No, not matter. So the dark energy is sometimes we call vacuum energy, or we call cosmological constant. Okay, and that is energy density. And when the universe grows by many times doubling, that is more or less constant. Now, the same constant density times the volume, you can see a huge amount. But universe is curved, so you can't talk about energy conservation. But then universe become our today universe, then you can talk about energy conservation. So beginning, you have absolutely no energy, nothing, no space, so no energy. And then today, the total energy must be zero. Okay? And because the gravitational field is negative energy, so one can easily convince oneself the total energy of universe at any moment, from a moment it's created to now to future, will be exactly zero.
Okay.
Now, by energy, I mean matter-energy conversion happen all the time. Okay, radiation, so there's a conversion all the time. But when I say total energy, I mean energy plus matter. But whenever you matter, multiply by c squared. You add up to be zero.
Okay, just one follow-up on that about the light thing. If I saw it correctly, you're implying that the observable universe was only a fraction of the size of the universe?
Yeah, tiny fraction.
I want to understand that, or maybe people miss this. We were all told about how the speed of light is the maximum. So in the inflation, is the universe is inflating faster than the speed of light?
Very
is that
good.
The point?
Yes, you make a very good point. So light can move at most the speed of light, which is finite. During inflation, the space being created, suppose I shine a beam of light towards you, okay? And during inflation, my beam of light will never reach you because the space being created between us is so fast, so much, that the light will not reach you until after inflation. So that means the space being created is so rapidly happening that light cannot reach you, but that doesn't violate the speed of light because these are new space.
The speed of light is based upon particles then, presumably, and not limited in the space concept then?
Well, yeah, because it takes certain time to come. No matter how fast it is, the space being created is faster. Okay. And that's no violation of any principle of relativity or quantum mechanics.
Okay, thanks.
So thanks for the important point. This is very amazing, yes.
Yes, here in the front. It's quick.
I was amazed by your presentation, especially when you mentioned that everything comes from nothing. Well, whether that statement represents a conclusion or still a hypothesis, I find a great similarity between that statement and the Taoist concept of wu, nothingness. Well, that really encouraged me to ask you the layman question that why do scientists ever study such topics as the origin of the universe, the operation of the universe? I'm from the humanities, to be more accurate, philosophy. And for people studying philosophy or professional philosophers, the inquiry into the origin of the universe is to find out how things originally or initially were. And the reason for asking such a question is not only for the sake of satisfying our curiosity, but also to derive from it some moral lesson or moral guidance. What guidance is it? That is guidance according to how we should lead our life. Well, and philosophy seems to believe that there is a certain relationship between how things originally were and how things should be. So because of such a belief, in search of the moral guidelines that they should follow, they begin the exploration to the origin of the universe. I just wonder whether you would like to share with the people in the humanities.
I apologize. I'm not a philosopher or moralist. I'm a scientist. So when we first look into this, we just follow the logic of the physics. And then when the logic of physics take up to order 10 to the minus 35 seconds, I mean, it boggles our mind. We are dazed, we're surprised too. I mean, but the equations are there, the physics are there, we just have to follow it to the end. And our job as scientists today is, once we have formulated a philosophical question, we try to find ways to test it. And only when we find ways to test it, then we consider science. So the line between philosophy and science is it's a moving boundary. And I would say the same thing between religion and philosophy. So, but religion is, you don't have to follow complete logical deduction. But I would like to have good religion which at least obey what we know about science. But the question you ask is much more difficult than the topic I talk about today.
So it's over here, please. Any students? Okay, feel free.
Today we have matter around us, so we can talk about gravitational potential energy, which is negative. But what about the period just before the inflation? I mean, during the inflation, there was no matter around us. So
yeah. During inflation, even you start with some matter, they very quickly be inflated away, like monopole or whatever. Okay, so essentially you have no matter, and then universe, no temperature, just dark energy, and then that just grow for doubling 50, doubling 60, 70, actually probably 80 times, roughly to 100 times, and then it ends. That's it. Okay. So during that time, universe, no temperature, no, it's very peaceful actually.
So what about energy conservation?
As I said, the problem is that during that time, universe is curved. So you have to include the curvature, curved space-time into the energy conservation. So you're really much more meaningful if you ask beginning and today, okay? So, and then in between, you follow the equation of general relativity. So beginning, there's nothing. So today, the total energy must be 0. By 0, I mean, in terms of percentage, it's 10 to the minus 100 something. So it's essentially totally absolute 0. I believe it's absolutely 0.
So one last question. At the end, you showed us like, so at our end will be like the whole universe being covered with dark energy. And that period will be almost flat universe, right?
Yeah.
So how do we consider energy conservation during that period?
Oh, that's okay. It's universes still have a curvature. So, because when you have little dark energy, that will introduce some not the curvature of space-time, but rather that space. It's what we call de Sitter space. So it has its very own boundary, own property. But I don't know if that's true or not. Okay, that's the most conservative belief is that they will go on forever, but people will come up with other scenarios. But predicting future is much harder because you can't do experiment to test it. Predicting past, that's random, a lot of debris or relics left behind that we can go and measure and test it. So in some sense, talk about future, that's more philosophical. Talk about past, there's a good chance that will be a scientific issue. So.
Okay, there's a question from the floor.
Thank you for the talk. I'm an engineer, so I'll ask a more practical question. You talk about the monopoles. So if we actually discover the monopoles, will that lead to a collapse of the Maxwell's 4 equations, which we use daily in electromagnetics?
Oh, if we discover a monopole, that we can do a lot of good things with it. All you need to discover one.
So, but would that lead to the collapse of the equations? Because
no, it would be perfectly fine.
Okay.
Equation will be perfectly fine. Although the so-called Maxwell equation has been changed a little bit.
Okay, we have to change it.
Yes, but that's a minor change as far as Maxwell equation goes. But if you introduce instead of electromagnetic field, but the gauge potential, then that's a little bit more difficult. But it's totally consistent if tomorrow one of you find a magnetic monopole. That will make front page to every single newspaper.
And business
Yeah, I think
opportunities. Some more questions? Any students?
think
Feel
that's
free.
fair.
Anybody? Okay. I think you're, oh yeah, over here. Reluctant.
Well, this is also coming from the humanities, but I just wanted to say that I was reminded of the playwright Beckett. He says, "Fail again, fail better." But there's something about your talk. I mean, there's a kind of modesty in science that is, quite wonderful because you all build on each other's work, and no one's ever right. Even Einstein. You just keep refining and coming up with new problems that you attempt to solve, knowing that there will be others along the way in a much, much bigger picture. That's kind of something very beautiful about that.
Well, thanks. I think when we work on this science, sometimes we are dazed by all these formulas. Sometimes the result is totally surprising. You couldn't believe the first time, but after looking at day in, day out for a while, you begin to accept it. But I think that, to me, I feel there's some beauty in it. So maybe not as apparent as music, but I think there's some intrinsic beauty in it, which a few of us can appreciate. So, and I hope that some of the general properties people not working in the field can also appreciate. So,
I can't think of a better way to end. So let's thank Professor Tai.